Okay, well, I'm George Bourianoff from Intel. I think I need to make one qualifying statement right up front here, since this is supposed to be a session on real-world electronics. Part of what I'm going to tell you is real-world, very much in existence today, but part of it is off in the future, so it's going to be a composite, but it's all going to be related to how we view the future of energy scaling in computing. The key messages that I want to leave you with at the end of this is, first of all, to extend Moore's law, energy scaling is a very, very real component. Perhaps it's impossible to say what the most important component is, but energy scaling is clearly one of the things we're going to have to master in order to keep Moore's law going. And the second thing is that Intel is making steady progress in more or less and scaling the existing paradigm, if you will. Taking today's devices, making them better in various ways by using different materials, different structures, and also just continuing to reduce the size dimensionally. But as we all know, they're getting small enough now that we're not going to be able to do that indefinitely. So we're looking to some of the other aspects of new materials and new structures to keep that going. But we're also looking, especially in collaboration with our university research partners, in longer range alternatives to keep the energy scaling going down and the performance going up. So my outline today, the things I'm going to talk about, is basically divided up into two pieces. First of all, I'm going to talk about the steady progress we're making in low-power CMOS devices. This is scaling the existing paradigm. I'm then going to move on and talk about some of the exploration of low-power beyond CMOS technologies, particularly spin devices, phase change devices, and something really different called pseudo-spintronics. But like Mike has to have his bubble charts, being from Intel, I have to have my Moore's law chart. So but this is going to have a slightly different twist to it. We all know that basically the number of devices integrated on a single substrate has gone up dramatically, 6 orders of magnitude in the last 30 years or so. And you're used to seeing over on this scale a figure of merit having to do with cost per functionality. But if you plot energy per function, you'll see it is also scaling down. Now, it has a few bumps in the road here corresponding to some of the transitions that Mike showed you earlier, but still the overall trend is clearly down, and over the course of 30 years, it's also been approximately 6 orders of magnitude. And of course, to keep Moore's law scaling forward, we're going to have to keep that going down. So where is the power being spent? If you go back to 2002 and work out and ask yourself, what did it take for 4 teraflops of computing power? This is basically 25 racks. It takes up 1,000 square feet, but a whopping 128 kilowatts of power to run this data center. 5 years later, we pack all that power, the 3.7 teraflops of computing power, into one rack with 40 square feet and 21 kilowatts. Now, I don't want to minimize the engineering difficulty of getting 21 kilowatts of power into one rack and getting that much heat out of that rack, but it can be done, and it is being done. But what I would call attention to is this rather remarkable drop in energy required. This is total wall plug power to run these things, including cooling, actually. So this has actually happened in the last 5 years, and I'm going to I'll give you a little bit of insights as to where that came from. But also, even though the data center is probably one of the easier things to visualize simply because it's so big and concentrated, like some of the other speakers have noticed, where we really spend most of our power is in PC and monitors. That's approximately 40% of the total energy spent on computation, including telecoms. The servers are 23%, but this is 40%. So like some of the other speakers have noted, this is where the opportunity is for reducing overall power consumption in computing. You can also try to analyze that by platform type. If you take basically a standardized workload for an average PC user going through the same set of applications, it turns out to make a big difference what platform they do it on. If you take a standard desktop unit, in this case a Pentium D processor, with a CRT display, it takes roughly 1,000 kilowatt hours per year to do what the average consumer does. It's not negligible. At 10 cents per kilowatt hour, that's about $100 a year for power just to power the PC. If you go to an LCD display, this comes down. But then if you start going to some of the more advanced power management technologies, like the new Pentium Core Duo, which has a managed supply. In other words, the voltage is changed with the different blocks to allow optimal power performance for a given application. And then if you integrate that with basically an integrated display, this can come down to 38. So there's a remarkable 26x reduction possible for doing the same set of things, but just on more efficient platforms. But I also need to say, in the interest of full disclosure, that if you look at where the power in the PC is going, at least 50% of it is going to interconnects. And given the current technologies, approximately 30% or a third is going to the actual devices, the actual processors. However, I'm going to focus in on this part of it, not because that's more important than the others, but that's just where I can point to some of the more significant progress in the last few years. So I'm now going to talk about the steady progress, the evolutional scaling of the existing paradigm. And the first thing I'm going to talk about is introducing high K metal gate. Now, just so, in case of somebody in the audience who doesn't know really the problem here, as you dimensionally scale the transistors down, the thickness of the gate oxide, which gets below a nanometer, which fits between the channel and the gate, gets down to dimensionalities of something like a nanometer or less. And therefore, given the fact that it's only 3 atomic spacings wide, it gets very difficult to maintain the quality and maintain the off-state leakage. In order to address that problem, you have to go to a different insulating material to give you a high K, where you get basically a bigger thickness, but the same electrical oxide thickness or decreasing electrical oxide thickness. And this has been known for many years, but it was a huge technological problem to find the high K material that would be consistent with the silicon stack, so that it would not decrease the mobility in the silicon channel appreciably, and also with the rest of technology to get this high K. So, and at the same time we were doing that, we decided to introduce metal gates for various reasons that made that task easier. So this was a huge technology step, which has occurred, I think, at the end of 2007. We introduced the metal K high gate devices. But also in parallel, we were introducing strain. So the idea with strain, of course, is by straining the channel, you can increase the mobility of the silicon. This is a concept, of course, originated at Stanford and at MIT. But again, implementing it in the laboratory is different from implementing it in mass production. So that we brought out in early 2008. Later in 2008, we married the two technologies, the high K metal gate with the third generation strain, the biaxial strain, in the 45 nanometer high K metal gate device. And that has led to some real performance requirements. If you look at the basically the ion versus the source drain leakage, what you see is a dramatic decrease in the source drain leakage, which was the primary, which is a significant component of the overall off-state leakage power. By going to this new technology, we could get basically a 5x reduction in the source drain or 10x in the gate leakage. And that by itself was a major step in advancing power-efficient computing by scaling of the current existing technology. And what they actually look like is really quite remarkable. At 45 nanometers, you see the high K gate dielectric there, the channel, you see the silicon germanium strain elements, and you see the metal gate, all of which integrated together to give you the performance that I just saw. But this is not radically new. This is basically using structures, FET structures that look a lot the same. It's reducing the size and introducing the new materials to make it, to get the factor of 5, which is, no one is downgrading the significance of the factor of 5, but the next factor of 5 will be probably harder to come by. So given that, we started looking at, in addition to working with silicon channels, we can work with high K channels. And that's, we all know that basically some of the 3,5 materials have a much higher electron mobility, especially than silicon. So that made an attractive target. However, introducing high K, introducing 3,5 channel materials into silicon posed a huge problem as far as matching the lattice constant between the silicon and the 3,5 material. So the key element there was to introduce a buffer layer between the 3,5 that could mitigate the defects that would normally be associated with the difference in lattice constants. In addition, we needed to have a conventional design and comparable density and cost. But all that was done for the N channel. Back in 2007, we basically demonstrated an indium gallium arsenide N channel quantum well FET, which basically has, again, a huge saving in the DC power consumption relative to silicon. If you look at basically the frequency response at a given power, you see a huge differential between the 3,5 device and the silicon device. So, but N channel was really the easier one to do. To get to the P channel, we had to go to a buried quantum well device, which was demonstrated IEDM 2008, and that also, but that gave us the P channel with indium antimonide as the composite structure. So by putting these two together, you have the potential for CMOS with N channel and P channel. With a rather complex structure, you get the performance. The trick is going to be to basically make these compatible dimensionally and cost-wise with scaled silicon, and that has not been done up to this time, but that's not to say it won't be done. We're working actively on that. So, as Mike Fritzy said, 3,5 materials are not the only materials with good mobility. Graphene is an obvious candidate, and so we've been working with Hanji Dai at Stanford to basically unroll nanotubes. Now the idea, of course, with graphene, it's a zero band gap material. So in order to get a band gap, you have to introduce quantum confinement. So Hanji basically has demonstrated how to make 7 nanometer wide nanoribbons, which have a moderate ion-I-off ratio and a backgated device. But that's a backgated device. It turns out whenever all the experiments up to very recently, whenever you try to put a top gate on it, it degrades the graphene mobility significantly. But at the University of Texas recently, they devised a methodology to put an aluminum oxide gate on top of graphene, aluminum oxide barrier on top, dielectric on top of graphene, and keeping the mobility above 6,000 centimeters per volt second. So that's really a significant accomplishment. We've already heard about the work to do CVD deposition onto silicon carbide in this case, but the idea is instead of doing Scotch tape method of putting down the graphene, how do you do it with a CVD process? So that's what was done here. These are the researchers at Purdue. I happen to quote here, but there are many people working on this. But the idea, again, is to get good quality graphene films with a manufacturable process onto manufacturable substrates. So in addition to graphene, there are carbon nanotubes. And this is some results coming from Ali Javi, who basically show a very, very promising carbon nanotube FET with some very nice characteristics. But this has to be done very carefully by selecting the nanotubes individually by hand and then positioning them and then very carefully attaching the source and drain. But if you do that, this shows the potential. This device, the fact that we could get this level of subthreshold slope, which implies low working voltages, this has tremendous possibility, although getting it into production is the outstanding challenge. But again, we're working with Philip Walling at Stanford, where he's demonstrated full wafer deposition of carbon nanotubes, aligned carbon nanotubes, transferred those to a silicon wafer with a transfer technique, aligned them, and then demonstrated basically a defect tolerant architecture where he exploits the advantage that you have by nanotubes being asymmetrical. They actually have much better properties one direction than the other direction. And by doing that, he can come up with circuits which are misalignment immune. And then we've heard some things about tunnel FETs. These are also very attractive devices. This is a recent calculation done at Purdue where they introduced scattering. And the net result of all this is including scattering properly in the computation gives you a much better, much more realistic result and can change the conclusions. What this shows, the net result here, these two curves in blue with the asterisks and the circles are with and without scattering. And the top graph here gives a MOSFET versus a tunnel FET. If you look over here, what you see is that introducing scattering to the model changes the qualitative conclusion that shows you can get better eye-on-eye-off ratios with a tunnel FET in a limited range of current. I think the consensus opinion is if you have to have high drive current, you're probably not going to be interested in a tunnel FET. But if you can live with a slightly lower on current, drive current, then there is a range in here where tunnel FETs appear to be a viable alternative. So now I'm going to talk some about the things that are not here today, some of the beyond CMOS devices which may use state variables other than electronics and different architectures. And the first thing I want to talk about are spin devices. Now, when you start talking about spin devices for computation, you have to bear in mind that they're the devices themselves that need to have some sort of switching capability. They have to have input and output devices to the rest of the world. They have to have interconnects, and you have to be able to put all that together in a useful fabric. So various devices with different functionalities are working on different elements of the overall picture of putting together a spin-based computing architecture. But the functionalities can be quite different, and when you look at the literature, you need to be aware of this. If you look at the dot-to-DOS device, for instance, basically you have a voltage modulating a current. The applied gate voltage will change the amount of current flowing through the channel. With the SPIN-FET by Sugihara and Tanaka, you're basically making use of some of the spin-dependent density of state properties of some of the half metals, which gives you an added switch to shut things off in principle. The spin gain transistor actually keeps a constant current, but it increases amplifies the spin polarization factor. You get interference devices for spin wave logic, and you get domain wall logic and through majority gate structures like this. But all these have to be developed more or less in parallel and deployed more or less in parallel to have any kind of spin-based computational structure. Just saying a couple of words about a few of the devices. The SPIN-FET by Sugihara and Tanaka basically has a conventional FET structure with a source and a drain, but the source and drain are half metal. And because of the spin-dependent density of states, it gives you an added magnetic shutoff factor in addition to the electrostatic barrier that you erect with straightforward FET operation. The idea is here, if you could get a good room temperature half metal source drains, you would be able to improve the ion-I-off ratio of the devices by doing so. A different idea is the spin gain transistor, where you're making use of the fact that various ferromagnetic semiconductors have a spontaneous ferromagnetic to paramagnetic transition at a constant temperature, just as a function of charge density. By manipulating the charge density in the base of this bipolar type structure, you can change the charge density in the base area and thereby induce a phase change from a magnetic state, paramagnetic state to a ferromagnetic state, and thereby amplify the spin current. 2 minutes? Okay. Then these are various amplifiers. We have to, for any kind of magnetic circuit, you have to be able to introduce gain into the circuit, and this is one way of doing that. This spin wave interference device is basically interfering the phase of applied waves. This spin wave, this is another amplifier technique where instead of, we use a magnetoelectric stack to modulate the B field applied to this ferromagnetic layer in here. But I think the most accessible and probably the most immediate use of spin to get to low power is to integrate some of these non-volatile magnetic elements with CMOS. And people at Hitachi published a paper where they did that integration successfully between a rather sophisticated MTJ and 190 nanometer CMOS process, where they got a dynamic power reduction of 80%, and the static power, of course, is reduced to 0. It's part of their normally off computing initiative that they've been working very hard on. This is another phase change device where we're coming out of Harvard. Here there's a field-induced metal insulator transition in vanadium oxide, which promises to be low energy because there's no conformational change of the crystal lattice structure. There's a similar phase change with basically a superlattice type structure with lanthanum, aluminum aluminate, and strontium titanate, where there's a two-dimensional electron gas formed at the interface, and you can change the properties of that very dramatically with an applied field. And this has been demonstrated experimentally since I put this talk together. The last slide is something completely different, which is a pseudo-spintronic device. The idea here is to form an Einstein-Bose condensate of holes on one layer and an Einstein-Bose condensate of electrons on the other layer. They will form an excitonic pair, which at zero applied voltage will, at any applied voltage, positive or negative, will maintain their excitonic relationship. But if the voltage goes to zero, if the bias goes to zero, then the conductivity between these two channels shoots up dramatically. Now that'll give you a very different type of IV curve than the one we're used to. But the interesting thing here is they predict 25 millivolt operation at 100 gigahertz or 5 attajoules per operation. So the conclusions are basically that Moore's law has demonstrated reduced energy levels over the past 30 years. To keep it going, we're going to have to find ways to manage the thermal, the energy consumption. We're working both on conventional extrapolation of conventional devices and also looking at some of the more novel devices which are out there. So that's.
Thanks, George. Time for some discussion before the break. Yeah, okay.
All the Einstein condensates usually require very low temperature.
In 3-5 materials, they do. In 3-5 materials, they do, and that's where they've been demonstrated. The hope is in bilayer graphene, the theory is that they will be room temperature. You can maintain the Bose-Einstein condensate because of the lattice, because of the fact that the lattice is very, very well formed. The theoretical predictions by MacDonald and the physicists associated with him is that you may be able to form these Bose-Einstein condensates at room temperature in bilayer graphene. And several groups are working on that to demonstrate that.
Over here.
So this is a question about spin logic devices. In MOS, in memory and logic took very different maturity curves.
It's the button on the bottom. Go ahead.
So in MOS, they took very different maturity curves. And I'm wondering that if you look at the STT RAM devices that are being claimed in maturity, in your assessment, compared to the spin logic versus the storage devices, how much is the gap? Should the system builders be worried about actually putting systems together with these new memory parts while the logic remains the same, or there is a 5 or 10 year horizon in which the two will converge?
Well, you notice they integrated the MTJ spin torque memories with 190 nanometer logic. And there's a reason for that, and that has to do with the maturity. The integration is a huge issue as far as processing temperature and materials. But the fact that they were able to do it successfully is a really significant data point. We've looked at it and think that we can carry that integration down to considerably further, perhaps as far as 65 nanometers with more or less existing technologies. Was that the question?
So if I'm a system builder, is it better to wait for intermediate solutions before going to STT RAMs in building systems?
You're talking about building general logic systems,
Non-volatile computing systems.
Yeah. If for general purpose, yes. If you're interested in the highest performance, no. But if you're interested in saving power with these non-volatile, by storing non-volatile states, I think I would you know, I think that technology will be on the market within probably 2 years.
Okay. Thank you.
Yeah. By the way, I'll go to Mark here, but I just wanted to mention, which wasn't what's on the agenda in your packets that we didn't have advertised earlier. At the end of the session tomorrow, at the end of the day tomorrow, starting at 2 o'clock, we plan to have a panel discussion where we can really bring all these different questions together at the system level, device level, and so please plan to stick around for that. Mark.
George, as you mentioned when you were talking about the conventional technology, a lot of the power is associated with the interconnection and basically driving signals across, because communication is very important in all these systems. So in the end thing, you talked a lot about spin devices, but communication for spin devices is always, at least as far as I know, is problematic. So is there some solution, or what is the assumed signaling method that you would use in the later technologies that you were describing?
Well, it's not nada. I mean, spin waves propagate in ferromagnetic materials. I mean, slowly but again, the fast, you know, it can be, what could be a bug could also be a feature. That if you actually pipeline things right, some people believe that that's slow propagation. There's actual processing you can do while the signal is propagating from point A to point B. And also, no.
I will just say that if you talk to systems people, I mean, if you talk to device people, they may say this is an attribute.
Mm-hmm.
If you talk to systems people and you say, do you want your signal to get from point A to point B now, or do you want it to be there later? I think everybody would say now. So,
Yeah, no, I think that we're all used to synchronous type operation, but so you'd certainly get into asynchronous type operation here. But
Okay, let me suggest we take that discussion into the break. I'll take one more question, though.
Thank you. It's connected to graphene. Actually, I'm now having here someone from the industry, and I would like to know that, or do you have a feeling how long it will take that graphene can really be made in a crystalline manner by MOCVD or MBE or something like that? Are you working hard on it to achieve that?
Well, the simple answer, do we know when it will happen?
Yeah, well,
No.
are you working on it at Intel, for instance? Very hard, with many people.
Well, I'm not sure what very hard is.
I mean, from the fundament, I can make it very dirty in this Scotch tape approach, but I would like to know if industry is doing it different way.
Well, unless someone makes 300 millimeter Scotch tape, I don't think that.
I think they make that, George. If Intel needed 300 millimeter Scotch tape, I guarantee you could get it.
I don't think. But no, it's a good question, and we're working on it. You know.
I mean, it's the most exciting material at the moment, apart from silicon, as far as I can see. I mean, it has opportunity for spin transport, which was discovered in my former group. Yeah, spin Hall effect is possible. I mean, it could be a new kind of electronics. And what do you think?
Carbon-based electronics has a lot of potential. It's got some problems, but I mean, it certainly has a lot of potential, and we're